Today we're going to talk about the solar system. We talked a little bit before about how the solar system was created, looking at the solar nebula hypothesis, where we had gases condensed and dust condensed into kind of a nebula or a cloud, and then in the center of that cloud, where the gases and dust were more concentrated, became our protosun, or protostar, and then around that, on the outside, there was a disk of gas and dust that started to swirl, started to condense. We had some of that gas and dust condensed into particles large enough to be called planetesimals. Those planetesimals collided into protoplanets and became protoplanets, and the protoplanets collided and accreted together to become our planets. Today we're going to look at a little bit about our different ideas of the solar system over time, and then we will also look at some basic characteristics of our planets and the movement of our objects in our solar system. So our first vision of our solar system as humanity, as far as humanity is concerned, was geocentric. Geo meaning Earth, center meaning centered. So it was an Earth-centered view. We thought we were at the center of the solar system, which, if you put yourself back 2,000 years, before there was technology, before we understood how things really are now, the way we understand them now, and you just were to look up at the sky, thinking that we're the center of the solar system isn't that unbelievable of an idea, because everything moves in relation to us. So it looks like everything's moving around Earth. So it's not really that, and things come back with the seasons and everything. So it's not that unreasonable of a thought in the absence of technology. So most of our ancient cultures did believe that everything kind of revolved around us. But it wasn't until the 2nd century BCE, so 4,000 years ago, when Ptolemy, who was an astronomer in the Middle East, really kind of laid down the tenets of the theory. And in the absence of technology, nobody really questioned this until about the 11th century. Now, in the Middle East, this is where a lot of our mathematics come from, in that area, and so there was a lot of development over the centuries in mathematics, and that's really where the challenges came from as we were moving towards the heliocentric or the sun-centered theory. They started to, as they developed better mathematics and they made better observations, even using the limited tools that they had at the time, they began to think that, you know what, maybe this isn't quite right. Really didn't explain why some of the planets seemed to move the way that they moved in relationship to the Earth. It just didn't seem to quite fit anymore. And so there were some of these different ideas that were kind of coming around between the 11th and the 16th centuries. Nicholas Copernicus was around in the 16th century, and he really kind of built on all of these different ideas from these different astronomers, and he built a new model for the solar system that was heliocentric. Helio meaning sun, centric once again meaning centered, so our sun-centered view of the solar system. And it seemed to make more sense because there are some planets that seem to have moved backwards, like Venus, which is called retrograde motion. And it doesn't really make any sense how Venus could move backwards and then forwards, and so this seemed to make mathematically a bit more sense. But at this time, the Catholic Church was in charge of most things in Europe. We're talking about the Middle Ages, so we're talking about the feudal systems, and we're talking about a time when the church had a lot of power. And saying that the sun was the center of the solar system went against the teachings of the Catholic Church. And so he was forced to recant his beliefs publicly, and his work wasn't published until actually after he passed away. Galileo, a bit later, about 100 years later, he confirmed the heliocentric view of the solar system. And he did this because now he had telescopes, and that was the big difference between Galileo and Copernicus, is that Copernicus was still looking at the skies just with his eyes, and Galileo now was able to see further into space than anyone ever had been before because of the very simple telescopes that he had. But this was still the time when the church was in power, and it still went against the church's teachings, and so Galileo was also forced to recant. He recanted publicly, but privately he started writing under like a pseudonym, and he started publishing pamphlets and things like that. So he never fully said, I don't believe in my theory anymore. But it wasn't until in the 2000s, actually, when the church apologized and said that, Galileo was right. So when we look at how society can influence scientific invention and exploration and innovation, this is definitely an example of a time when society and culture sort of hindered scientific progress because the people that were in power wanted to stay in power, and anything they saw as a threat to that power, they chose to suppress. And so it wasn't just this scientific exploration, it was a lot of scientific exploration that was suppressed at the time. So when we talk about the movement of the planets, move in two different ways. One way we move is through rotation. So we rotate on our axis, and this gives us day and night. We rotate once every 24 hours on our axis. And then, while we're still rotating our axis, we also revolve around the sun. So revolving around the sun takes 365 and 1/4 days. That's the reason why we have leap year every 4 years, is to make up for that extra quarter day each year. Otherwise, our calendar would kind of get out of whack. Revolving around the sun is how we get our seasons, based on where we're at around the sun and with the tilt of the planet. So two different motions. Make sure that you understand the words separately because they cannot be used interchangeably. Just a little look as they move around the sun. You'll see that the planets that are towards the center of the solar system, their orbit is shorter, so obviously it's going to take less time to go around the sun. But if you notice, they're also moving faster than the planets are away from the sun. And we're going to talk about why that is based on Kepler's laws of motion, planetary motion, here in just a few minutes. But I did want you to notice that. So here's Mercury, and look how fast Mercury is moving compared to, wait for it to come around, see how slow Neptune's moving, there it is. Okay, as it moves around. So the closer that you are to that center of gravity, the faster your motion is going to be. So we don't move in a perfect circle around the sun. We move in what's called an ellipse. Our placement in the ellipse has nothing to do with our seasons. So just so we make that one clear, it's about the tilt of the planet, not about where we're at in our orbit around the sun. It does mean that at certain times we're going to move faster, because in that time, when we're closest to the sun, or the perihelion, we're going to move faster, and during our aphelion, we're going to move a little bit slower. So we have this elliptical orbit, and you can see that the further away you get from the sun, the bigger the ellipse becomes. So it becomes more exaggerated, which is another reason why on this side, right, Jupiter's going to move much slower than it would over here on this side. So our planetary motion, once again, we've got our aphelion and our perihelion. Once again, nothing to do with the seasons on here. But Kepler's second law of motion says that if it's in an ellipse, we're not going to move at the same speed all the way around. We're going to move faster here, where we're closer to the center of gravity, than we are over here. In a lot of sci-fi shows, they keep talking about, oh, we want a slingshot around the sun, right, to do something, go back in time, or, build up speed or something like that. And the reason they say that is because as you go around the sun, if you go around closely around the sun like that, if you can escape the gravitational pull, it should make you move faster. And then we get into one of our other laws of motion that says that an object in motion stays in motion, right, unless something acts on it. The further away you get from gravity, the less there is to act on you, so it would make you go faster. So we talk about it with a rock or something like that. If you throw the rock up, it's going to move faster at the beginning and slower as it gets up towards the peak of its height, because as it gets up further away, it's escaped gravity, right, as it gets further up, but it's further away from that influence of the body, which is at that point Earth, which is exerting the gravitational pull. But it's very similar to how our sun and our planets act. So we have a constant amount of energy in the universe. So that means that you have two different kinds of energy. You have the energy of motion, which is kinetic energy, and you have stored energy, which is potential energy. So the kinetic energy is going to determine how fast the planet moves, and the potential energy is going to say that's how much stored energy is. So if you have greater potential energy, you're moving slower because more of that energy is stored up in you as opposed to being used in kinetic energy. So when you're close to the sun, you don't have a lot of potential energy, or when you're close to that center of gravity, you don't have a lot of potential energy because you're using most of it to move, and so the planet is moving quickly. The further you get away from the sun, you have more potential energy, which means the kinetic energy has to be has to be smaller because we have only so much energy available, and so your velocity is less. So our Newton's third law of motion says that an object in motion stays in motion. So once it starts moving around the sun, it's going to keep moving, but we say, well, why doesn't it just shoot off, right? And everybody knows, I think, that it's because of the gravitational pull of the sun, but it's really about inertia, which is Newton's first law. So we put things in motion, they're going to stay in motion unless something else acts on it. And the inertia in this point, or the thing that's acting upon the planet, is the gravitational pull of the sun. And so when you have the balance, the reason that we stay in the orbit that we're in is because you have the balance of the energy from the planet on its orbit around us that revolves around the sun. That's wanting the planet to move out, but the gravitational pull of the sun is pulling it in. It's kind of like if you've ever been on one of those carnival rides where you stand on it. Like when I was a kid, they called it the gravitron. You'd stand on it and it would spin and you'd like flatten up against the wall. And you could lift up your arms and stuff, but you kind of stuck to the wall. Okay, that centrifugal force, which is what's pushing you out, made you stay up against the walls. But the gravitational pull of the Earth is what made you not fall down on there. And it's kind of the same premise here. So as we're revolving around, we're spinning around. Okay, but the gravitational pull of the sun is holding us in. So it's that balance of the forces. All right, some characteristics of our planets. We have our terrestrial planets, or our inner planets. Once again, in the inner planets, they're rocky and they're solid. They have a much more metallic content or metal content to them, and that's because these materials and elements could stay solid at a higher temperature. It's closer to the sun, it's a higher temperature, so they were actually able to become solids, and they kind of gravitated towards there. Our terrestrial planets are the smallest of our planets, and that's because they're much more dense. So all the material got kind of compacted in because of the gravitational pull of the sun. Excuse me. So our innermost planet is Mercury. Mercury has really, really hot on one side that's facing the sun, not quite so hot on the side that's not facing the sun. It doesn't have an atmosphere. It's all pockmarked with craters from where it got hit, everything. And it actually is the smallest planet now that Pluto is considered a dwarf planet. It is the smallest planet in the solar system, closest to the sun. It doesn't have any rings or moons. There was no possibility that Mercury could exert a greater gravitational pull than the sun, and so there's no way to keep anything around Mercury. Our next one is Venus. Venus is most similar to Earth in size and composition. It doesn't have any rings or moons either. It does rotate backwards, which is called retrograde motion, which makes it look like it goes backwards across the sky, and that's why we call it that. There's a lot of methane in the atmosphere, which is why it's blue. It also causes the greenhouse effect. It also has a high content of carbon dioxide. So there's lots of acid rain on Venus, so we couldn't actually live there because there's no water that we could actually consume, and the atmosphere would be toxic to us. Earth is next. So we're the third planet of the sun. We also don't have rings or anything like that. We can support life. We've got liquid water at our surface. We've started to find some frozen water on Mars, but not yet the liquid. Mars comes next. Our fourth planet, the reddish color, comes because it has a lot of iron in the rocks and the materials, which oxidizes and becomes that reddish color. It does have big dust storm soups. They have found that ice at the polar regions And because of the Mars rovers, they've been able to discover a lot more about Mars. Once again, it also has, you can see all the craters on these different planets because there's no vegetation or anything to cover them up, and there's less erosion, and so the craters that were impacted even millions of years ago still show up because there's so little erosion and weathering that occurs, unlike here on Earth, where we have lots of water. In between, so as we go past Mars, we hit the asteroid belt. So the asteroid belt is a lot of chunks of rocks that didn't get incorporated into a planet. There's a couple of different theories about why that might have happened. One is that there actually was a planet there, and because of a collision between planets and asteroid or planet and another object, it actually pulverized the planet, and it did so at a time where everything had cooled down too much and it could no longer go back through the accretion process and become a planet again. Other theories are that it just was at that right distance that it couldn't, that it just didn't accrete into a planet. So it's pretty wide. This is where a lot of our meteors come from, is in this area. Asteroids can kind of run into one another because they're all out there, and it can knock one out of its orbit, and it can knock it closer to the sun so that it actually starts to get pulled in by the gravitational pull. And if it intersects with the orbit of Earth, that's where we can have some rather large impacts. The asteroid that hit the planet 65 million years ago was knocked out of the asteroid belt. So our next stop is our Jovian planets. So these are the larger of our planets. They're the gas giants. They're called that because they're primarily composed of gases. They do have a core, but you couldn't actually land on the surface of them. If you tried to, you just they kind of crash landed probes into Jupiter, and it just kind of kept going in until they lost contact with it as it kind of went down through the surface. So they're low in density because they're made out of gases, unlike the inner planets, which are mostly composed of rock type materials, and so they're very dense. So our first stop is Jupiter, the largest planet in our solar system. That red spot is a huge storm that's been going on for as long as we've been able to see Jupiter. It rotates around in the atmosphere. Once again, nothing breathable or usable for us, excuse me, and Jupiter. Next is Saturn. Saturn has our most clearly defined ring system out of any of the planets in our solar system. The better our telescopes have gotten, we've seen rings around some other planets that we'll talk about. It does have 31 moons, so it has a pretty complex system around it. As we got farther away, the reason why as our planets are further away, there was less gravitational pull from the sun, so there was more opportunity for moons to actually act on the to be attracted to the gravitational pull of the planet as opposed to the sun. We're going to go back just a second to Jupiter. So one last thing about Jupiter, and that is that Jupiter is so very like the sun, quite honestly, because of the amount of gases that are and the types of gases that are involved in creating Jupiter. All it needed was a bit more size, and Jupiter could have been its own sun. But because it's smaller, it's only about an eighth of the size of the sun, it didn't have the mass that it needed in order to jumpstart fusion in its core. So it was kind of like an almost protostar, but it won't ever become a star because it's not big enough. All right, from Saturn we move on to Uranus. So once again, once we get into the blue planets, there's lots of methane that are in there. This one is a little bit different. So when we think about our rotation on our axis, if you think about Earth and you hold your finger and point it up at the sky and tilt it just a little bit, Earth spins around your finger that way. But for Uranus, if you take your hand and you point your finger at the wall now and have your hand so that it's parallel to the floor, and now imagine that the planet is spinning around your finger the same way, that's how Uranus spins. So it doesn't spin the same way as the rest of them, which makes it a little bit unique. It does have a very faint ring system around it as well. And it has a bunch of moons. Neptune is our next stop. So we're getting way far away from the sun, which is why Neptune is so cold. Neptune has a blue spot, just like Jupiter has a red spot, and that's its massive storm. It's made a lot of methane as well. It does have a very faint ring system also. So we've got 3 planets that actually have ring systems. Pluto is the largest of our dwarf planets. So Pluto was actually discovered here in Arizona up at the Lowell Observatory in Flagstaff. Was kind of one of our claims to fame. They thought originally was classified as a planet, but in order to be considered a planet, you have to only revolve around the sun. So that's one of the parts of the definition of being a planet. Pluto and Charon, which is its sister, are actually like a binary planet system. So they revolve around one another, and then they also revolve around the sun. And because they revolve around one another, that excluded them from becoming a planet. There's also, as our telescopes and our exploration get they're finding many Pluto-like objects that are out in what's called the Kuiper Belt, which is the area that's out beyond Pluto that has pretty much all the leftover debris from the formation of the solar system that didn't get incorporated into the planets. So they're finding a lot of things that are Pluto-sized or pretty close to Pluto-sized out there, and so that's why they declassified Pluto as a planet.